All right, let's jump right into this explainer. Today we're unpacking something genuinely fascinating, the Mars architecture. We aren't just talking about another standard software app here. We're talking about an ultra-efficient, fully autonomous software factory. Now, if you've ever tried building multi-agent AI systems, you know the absolute headache it can be, right? Agents constantly stepping on each other's toes, massive context bloat that just burns through tokens and budget, and of course, agents getting stuck in those dreaded infinite loops where they just try to fix the same error over and over. Well, Mars is a system designed from the ground up to solve exactly those problems.
Here is our literal flight plan for today. We'll be hitting 1. The birth of a task, 2. Mapping the dependency graph, 3. The trust-based worker, 4. The autonomous review loop, 5. Multi-layered error handling, and finally, 6. The complete Mars lifecycle. Let's start tracking our data right down the assembly line.
Starting with Part 1, Birth of a Task, the planning phase. Mars uses what's called a two-stage execution pattern. So instead of throwing a massive goal at a basic agent and just crossing your fingers, a top-tier, expensive model steps in first to do all the heavy strategic thinking. It breaks the goal into subtasks and picks the right tools so the actual manual work can be handed off to much cheaper model.
Think about how we used to build agents versus the streamlined Mars approach. In the old, monolithic way, you'd hand a single agent the entire catalog of, say, 19 different tools. The result? Massive context bloat. We're talking around 7,000 to 8,000 tokens per single call. The Mars way completely changes the game by filtering that context. Because of that two-stage pattern, it selects only the 2 to 5 specific tools needed for that exact subtask. It slashes the token count down to around 500 tokens. Literally a game changer for efficiency.
Moving right along to Part 2, mapping the dependency graph, the routing phase. Okay, so once those subtasks are created, how do we run them quickly without them bumping into each other on the factory floor? How do we maximize parallel execution, but safely?
The secret sauce here is a DAG, or a Directed Acyclic Graph. The central task processor in Mars analyzes the dependencies between all the generated subtasks, and the DAG strictly maps out what needs to happen first, second, and third. Crucially, it ensures there are zero circular dependencies, meaning no situations where task A is waiting for task B, while task B is waiting for task A. By mapping this mathematically, Mars knows exactly which independent subtasks can be fired off at the exact same time.
This leads straight into Mars's wave-based execution, and the rules here are ironclad. Step 1. Tasks absolutely must wait until all their specific prerequisites are fully met. Step 2. Once ready, all independent tasks launch simultaneously in a concurrent wave. Step 3. The next wave will not start until the current one finishes completely. And Step 4. If a dependency fails, it intelligently halts any downstream tasks that relied on it. It is perfectly orchestrated traffic control.
Which brings us to Part 3, the trust-based worker, the execution phase. Now we're hitting the actual factory floor, where the specialized swarm worker takes over to build what the strategic layer just planned out.
The big takeaway here is this massive 75 to 90% token reduction we see in execution. I mean, that is a staggering drop. And it happens precisely because the worker isn't bogged down with unnecessary tools or big picture strategy. It doesn't need the grand vision. It just needs to do its specific job really, really well.
Mars calls this the trust-based worker pattern. These workers receive a dynamically created filtered Pydantic AI agent, and they only have access to those 2 to 5 specific tools we mentioned earlier. Most importantly, they blindly trust the central task processor's strategy. They do not go rogue, they don't try to replan or pick different tools. Their only job is to generate the literal parameter values and execute. It creates this beautifully simple stateless execution loop.
Okay, the task is done, but do they actually write working code? Let's get into Part 4, the autonomous review loop, the QA phase.
What's super fascinating here is that QA happens without ever blocking the workers. You have this background review processor constantly pulling the Redis queues for completed tasks. And it is Git aware. It independently fetches the exact Git commit diffs tied to the worker's output. Then, it evaluates the code using hard static analysis combined with an LLM as a judge to score the result. So the worker just moves on to its next job while the judge handles the review.
But that brings up a massive challenge, right? Think about the biggest risk of autonomous retry loops. What happens if an agent makes a mistake, the judge rejects it, and the agent tries to fix it by doing the exact same wrong thing? Getting stuck in an endless loop like that will drain your API budget in a matter of minutes.
Well, Mars actually calculates loop limits in line, based on the real complexity of the task itself. It uses this clever Bayes formula, 3 plus the task's complexity score times 2. So, naturally, harder tasks get more tries, but there's a strict ceiling. It is hard-capped at 9 attempts to protect your resources. And if the judge rejects the work, it doesn't just yell, "Try again." It enriches the task with detailed feedback, flags it as needs revision, and sends it back so the next attempt is fully informed by the critique.
Now, even in the best, most highly regulated factories, things break. APIs go down, network errors happen. So let's look at Part 5, Multi-Layered Error Handling, the safety net.
Mars catches errors across 3 distinct layers of defense. Down at the base agent layer, using Pydantic AI, it gets 3 immediate attempts to fix validation errors, like if the LLM spits out bad JSON. Moving up a level to the infrastructure layer, the Unified Retry Manager handles transient network errors and API rate limits with up to 10 attempts using exponential backoff. And finally at the top, we have that review layer we just talked about, using complexity-based loops to handle the actual code quality and logic failures.
All right, let's pull all these pieces together for Part 6, the complete Mars lifecycle, end to end, and witness the full data flow in action.
This timeline is the strict state machine of a single task, anchoring its exact journey. It's born as created when the strategic planner breaks down the goal. It moves to pending once it hits the reddest priority queue. When a worker grabs it, it's actively processing. After it's built, it hits pending review. And only when the autonomous judge fully approves the work does it finally reach that ultimate completed terminal state.
And running silently underneath all of this is version control. Because every single action a worker takes is tied directly to a specific git commit SHA, this whole autonomous factory is fully auditable. If a task somehow goes completely off the rails, the system gives you reproducible rollbacks. You can literally trace any result back to the exact file state at the exact moment it happened.
Which brings us to a pretty profound question to wrap up. Architectures like Mars are fundamentally redefining development. If your AI agents can now seamlessly handle strategy, execute safely in parallel without stepping on toes, independently judge their own code, and fix errors in a smart feedback loop, what actually limits the scale of the software you can build today? It's an incredible paradigm shift. Thanks so much for joining me on this explainer, and I hope it gave you a really clear window into how autonomous agent orchestration is evolving.